Welcome to the Windshear and Microburst lesson. In this lesson, we will discuss the general characteristics of windshear and microbursts. In addition, we will discuss methods for windshear detection, prevention, and recovery. Windshear is a sudden drastic change in wind speed or direction over a short distance. While wind shear can occur at any altitude, low-level wind shear is especially hazardous due to the aircraft's proximity to the ground. Low-level wind shear has been known to produce directional wind changes of 180 degrees and speed changes of 50 knots or more. A wind shear as a result of an increasing headwind increases indicated airspeed and thus increases performance. Increasing headwind wind shear may precede a more hazardous increasing tailwind shear. An increasing tailwind shear decreases airspeed and performance. Due to airspeed loss, the airplane may tend to pitch down, causing additional altitude loss. Wind shear hazards can be minimized by early recognition, recovery techniques, and most importantly, avoidance. Watching for indications of potential wind shear conditions improves awareness and reduces the risk of a wind shear encounter. During each phase of flight, evaluate the weather and decide if it is safe to continue based on the number of indications for possible wind shear. Indications for possible wind shear include a thunderstorm cell over or near the flight path within 5 miles of the airport. Virga when the surface temperature exceeds 27 degrees Celsius with a dew point of 5 degrees Celsius or less. ATC broadcasted wind shear alerts or advisories. Pilot reports of airspeed loss on final approach or takeoff. Variable or gusting winds, even in predominantly light winds. Blowing dust or swaying treetops near the airport. And dust devils. Because of the hazards to aircraft operations at low altitudes, pilots are urged to promptly report any wind shear conditions they encounter. An advance warning of this information assists other pilots in avoiding or coping with wind shear, especially on approach or during departure. When describing wind shear conditions, use of the terms negative or positive should be avoided. For example, reports of negative wind shear on final can be interpreted to mean that no wind shear was encountered. The recommended method for wind shear reporting is to state the loss or gain of airspeed and the altitudes at which it was encountered. For example,
Tulsa Tower, American 1721 encountered wind shear on final, gained 25 knots between 600 and 400 feet, followed by a loss of 40 knots between 400 feet and the surface.
Another hazard associated with convective weather, which can cause wind shear, is known as a microburst. Microbursts are small-scale, intense downdrafts, which extend to the ground and then spread out in all directions. A microburst downdraft is typically less than 1 mile in diameter as it descends from the cloud base to 1,000 to 3,000 feet above the ground. In the transition zone near the ground, the downdraft changes to a horizontal movement of air that can extend up to 3 miles in diameter. The downdrafts can be as strong as 6,000 feet per minute. Horizontal winds near the surface can be as strong as 45 knots, resulting in a 90-knot shear across the microburst. These strong horizontal winds normally occur within a few hundred feet from the ground. Microbursts can be found almost anywhere that there is convective activity. They may be embedded in heavy rain associated with a thunderstorm, or in virga that may appear harmless. When there is little or no precipitation at the surface accompanying the microburst, a ring of blowing dust may be the only visual cue of its presence. An individual microburst seldom lasts longer than 15 minutes, from the time it strikes the ground until dissipation. The horizontal wind speed increases during the first 5 minutes, with the maximum intensity wind lasting approximately 2 to 4 minutes. Sometimes, multiple microbursts are concentrated into a line structure, and under these conditions, activity may continue for as long as an hour. Once microburst activity starts, multiple microbursts in the same general area are not uncommon and should be expected. During inadvertent flight into a microburst, the aircraft first experiences a performance-increasing headwind, followed by performance-decreasing downdrafts. Then, the wind rapidly shears to a tailwind. The airspeed rapidly decreases, causing a further decrease in performance. This can result in altitude changes that may bring the aircraft dangerously close to the ground. Several systems exist to alert pilots of microburst and wind shear activity. The warnings provided by these systems are transmitted to pilots by ATC and flight service stations. The most popular systems include Low-Level Wind Shear Alert Systems, or LWAS, Terminal Doppler Weather Radars, or TDWRs, and Weather Systems Processors, or WSPs. LWAS detects the presence of hazardous wind shear and microbursts in the vicinity of an airport. Wind sensors, mounted on poles, sometimes as high as 150 feet, are located 2,000 to 3,500 feet from the center line of the runway. When wind speed changes that exceed 15 knots are detected, a warning for wind shear is issued by the system. TDWRs are designed to monitor the airspace around an airport to detect microbursts, gust fronts, wind shifts, and differences in precipitation intensities. This radar system monitors all runways and the areas 1/2 mile on either side of the extended centerline, out to 3 miles on final approach, and 2 miles on departure. The purpose of the WSP system is to provide wind shear detection at medium air traffic density airports not equipped with a TDWR. WSP has advantages over the Terminal Doppler Weather Radar, as it can be installed on existing airport surveillance radar and can be located closer to runways. As a precaution for takeoff during possible wind shear, plan to use maximum rated takeoff thrust. This shortens the takeoff roll and reduces the risk of overrun. This thrust setting also provides the best rate of climb, thus increasing altitude available for recovery if required. Another precaution is to use the longest suitable runway that avoids suspected areas of wind shear. This assures maximum runway available to accelerate to rotation speed. A longer runway will also provide more ground clearance at the end of the runway and during the climb profile. Should the decision be made to reject the takeoff, a lengthy runway provides a greater distance to stop the airplane. Depending on the aircraft type, different flap settings should be considered unless the takeoff is limited by obstacle clearance or climb gradient. Plan on an increased airspeed at rotation to improve the chances of recovery if wind shear is encountered. However, overrun exposure may be increased if the wind shear reduces the airspeed below the minimum airspeed required for liftoff. To help protect against runway overrun, plan to initiate rotation no later than 2,000 feet from the end of the usable runway. If wind shear is expected during approach and landing, a stabilized approach should be established no later than 1,000 feet AGL to improve the margin of safety. When preparing for the approach, the following flap settings should be considered. During approach, rather than immediately compensating for an airspeed increase by reducing thrust, a brief pause to evaluate speed trends is prudent. Plan on using a longer runway to provide the greatest margin for an increased ground roll due to unanticipated winds and high ground speed at touchdown. If available landing field length permits, airspeed may be increased up to a maximum of 20 knots. If approach speed is increased, plan on touchdown to occur within the normal touchdown zone. Do not allow the airplane to float down the runway. Flight crew awareness and coordination is essential for prompt wind shear recognition and recovery. It is important to remain alert for any change in conditions, as wind shear can be quick to form and dissipate. Time available for recognition and recovery is short. Crews should be aware of normal vertical flight path indications so that wind shear-induced deviations can be quickly recognized. During takeoff and approach, be alert for airspeed fluctuations. Such fluctuations may be the first indication of wind shear. During takeoff, unusual airspeed fluctuations or slow or erratic airspeed changes may be indications of possible wind shear. In this example, an increasing tailwind shear is encountered. If unacceptable airspeed variations occur at speeds below V1, and there is sufficient runway remaining to stop the airplane, the takeoff should be rejected. The takeoff must be continued if V1 has been reached. In severe wind shear encounters, rotation speed might not be reached, and the option to reject the takeoff may not exist. If this is the case, rotation must be initiated no later than 2,000 feet from the end of the usable runway surface. Pitch attitude and rotation rate should not be restricted to avoid a tail strike, since a higher pitch attitude may be required to lift off in the available runway distance. If rotation speed is reached during the takeoff roll, rotate at normal rate towards 15 degrees pitch attitude and increase thrust. Pilot technique for recovery must be a combination of both thrust and pitch. Thrust alone may not be sufficient to offset the effects of a wind shear encounter. Avoid engine overboost unless it is necessary to ensure airplane safety. Once airborne, follow the after liftoff recovery technique described in the next section. Additional wind shear considerations during takeoff include the following. Timely recognition of wind shear encounters on the runway may be difficult since the only indication may be a slower than normal airspeed increase. The go, no-go criteria based on engine failure decision speed, known as V1, may not be valid for wind shear conditions, since ground speed can be much higher than airspeed. The ability to lift off is a function of airspeed. The ability to stop is largely a function of ground speed. It therefore may not be possible to stop the airplane on the runway during a rejected takeoff. The recommended recovery procedure for wind shear in flight should be immediately initiated anytime the flight path deviates below 1,000 feet AGL during climb or approach and wind shear is encountered. Crews should be prepared to execute an immediate wind shear recovery if deviations as a result of wind shear exceed the following. During climb, greater than a 15-knot deviation in airspeed, greater than a 500 foot per minute deviation in vertical speed, or greater than a 5-degree deviation in pitch attitude. During approach, execute a wind shear recovery if you experience greater than a 15-knot deviation in airspeed, greater than a 500 foot per minute deviation in vertical speed, greater than a 5-degree deviation in pitch attitude, greater than a 1-dot glide slope displacement, or an unusual thrust position for a significant period of time. Now let's take a look at the in-flight wind shear recovery procedure. These procedures can be applied during both climb and approach. Aggressively apply necessary thrust to ensure adequate airplane performance. Disengage the autothrottle if necessary. And avoid engine overboost unless required to avoid ground contact. If ground contact is imminent, use full available thrust. When airplane safety is ensured, adjust thrust to maintain engine parameters within specified limits. At a normal rate, increase or decrease pitch attitude as necessary toward an initial target attitude of 15 degrees. The autopilot and flight director should be turned off unless it is specifically designed for operations in wind shear. Use intermittent stick shaker as an indication of the upper pitch limit. During severe wind shear, the stick shaker may occur below a 15-degree pitch attitude. If the aircraft attitude has been limited to less than 15 degrees to stop the stick shaker, increase the attitude toward 15 degrees as soon as the stick shaker stops. If the vertical flight path or altitude loss is still unacceptable after reaching 15 degrees, increase pitch attitude further in small increments. Once the airplane is climbing and ground contact is no longer an immediate concern, airspeed should be increased by making small reductions in pitch attitude. Flap and gear configuration should not be changed until terrain clearance is assured and the aircraft is clear of the wind shear. Although a small performance increase is available after landing gear retraction, initial performance degradation may occur when landing gear doors open for retraction. Similarly, although extending flaps during a recovery after liftoff may result in a performance increase, it is not a recommended technique or procedure. It may result in accidentally retracting the flaps with a resultant adverse impact on performance. If autopilot and flight director systems specifically designed for operation in wind shear are engaged during approach, they should be used during the recovery maneuver. However, if these systems were not engaged prior to the onset of wind shear, do not engage them during the recovery.
That is incorrect. That is correct. That is incorrect. That is incorrect.